with the material for today. I'm going to actually do an end to the story that we started last time, and then we'll move into the new material. Hold on, it's warm. All right, my mask will not stay on my nose because I have a beard underneath it, so just my apologies if it keeps sneaking out. I'll try and put it back. Okay, so I want to give you a few various properties of these Sturm-Liouville systems that we were talking about last time. Starting with the eigenvalues. So these are SL systems of polynomials. So for eigenvalues, we know that all of these equations can be written as an eigenvector equation. And I'm talking in general about Sturm-Liouville systems, so I'm not necessarily talking about Legendre, Laguerre, Jacobi, whatever. This is just generic. Okay? So remember the form of the operator for the polynomial systems, which is what we really focused on, is the following. Okay, and now what we can say is we know that, you know, everything in here is a polynomial. So when you have a polynomial equation, of course, one of the important aspects of it is that all the coefficients from, say, x to the n have to satisfy the equation on their own. So if we go through this expression and we gather all of the contributions to coefficients of x to the n, then we get something like the following. Alpha naught n minus 1, which comes, of course, from taking the second derivative of this function, which has a maximum power of x to the n, so that brings it down to n minus 2. And then you restore it with that x squared. So that's why you got alpha naught n times n minus 1 from taking the two derivatives. And then from this guy, you take one derivative and then restore it with the x. And so you get beta naught n equals lambda n, which we can also write as n alpha naught n plus beta naught minus alpha naught. And then the interesting observation that's made in the book is that the lambda n's are spaced linearly for alpha 0 equals 0. Okay, these are the Hermite and the Laguerre polynomials as examples, whereas they're spaced quadratically when alpha naught is not equal to 0, and this, of course, is the Jacobi polynomials. Okay? So eigenvalues are one interesting observation. Now, for the Rodriguez, recall that we were introduced to these Rodriguez functions, which lets you evaluate the polynomials. Okay, and here we have Wx equals 1. Here we have Wx. This is the weight and the inner product, of course, minus x. And then in this case, we have Wx is e to the minus x. Okay. And these are, of course, Legendre, Hermite, and Laguerre polynomials. If you look at those expressions for a minute, can you see a common theme? Anyone? Bueller? Bueller?
Yeah.
Bueller.
They all have the weight function in them?
They have the weight function. Well, look at this. This has definitely got a 1 in it.
Yeah.
It's there. It's there. It's there. It's there. It's everywhere. You can stick a 1 anywhere. Here, though, notice e to the minus x squared. It's in there. And here, e to the minus x is in there. I mean, they're functions and their inverses, okay? So it turns out that you can write down a generic form of the Rodriguez formula. And it takes the following form. First of all, there's just some overall constant. Okay, that's not that functionally important. And then what we find is the following. Okay, this is not a label, this is a power. Okay? All right. And then last but not least, we have completeness. And we'll start this off with a theorem. And I'll try and use as brief a notation as humanly possible. Of course, I probably could have written the word orthonormal, and that's not even what that means. Shit. The orthonormal. Now, how would you illustrate orthonormal? Because this is obviously orthogonal, right?
It's a magnitude lines around or something. There you go. Look at that. There
I think I could write the word orthonormal by the time I get that. But that's cute. It's very cute. Anyway, all right. So orthonormal set of Sturm-Liouville polys. Q and X is complete in Hilbert space. This, of course, is a theorem, which, of course, means it could and should be proved. So let's prove it. All right. Now, I'm going to go through this proof, and I'm actually going to go through a very similar proof a little later in the lecture. I just want you to get a sense that a lot of these proofs actually entail the same steps. We want to prove that something is complete. Lucas, if we want to prove something is complete, what is another thing that we can prove that leads to it also being complete? That's a definition of what completeness is, but when we're proving things, I've done proofs like this before. So what property can you attribute to a system which immediately implies its completeness? It starts with a C. Sorry, say it again?
Convergence, uniform, or Pointwise convergence.
So there are convergence issues as well, but that's not what I have in mind. Joel?
I mean, it's the one with the integral, the inner product of a function being 0 implies that the function is 0.
And we call that what? Closed. Okay? All right, so so remember closed
When's the midterm?
implies complete. That's fine, don't work, I mean, look, this stuff has just, you know. But I'm gonna do two of these today, so hopefully at the end of today's lecture, you'll be like, I'm kind of comfortable with that proof. Okay, so if something is complete, if something is closed, then it's complete, so all we really need to do is prove that it's closed, and it's closed if f, the inner product of f with the qn's, this is any of the elements of this set, equals 0, implies that f equals 0 almost everywhere. Okay? And almost everywhere, you remember when we introduced the Lebesgue measure for integrals. So just there are a few functions which are just non-zero for points that can be effectively called 0 almost everywhere. And their integral under the Lebesgue measure is 0 as well. Okay, so here we go. All right, now first of all, the qn's are polynomials in x, and that means that you can write any power of x as a superposition of the qm's. Okay? Does that make sense? Now what that implies is that if qn equals 0, so too does fxm. Okay? So one can argue that if fqn equals 0, then fxm is 0, and again, this should imply for a closed system that f equals 0 almost everywhere. All right. And again, this is for all m. This is for all powers of m. All right, so here we go. What we're going to do is we're going to consider, I'll just do this up here so I'm not squatting down. We can consider the following. GK is the inner product of e to the ikx with f. Okay? Now, I should say this is the point where the proofs are going to differ between what I'm doing now and what I'm doing next time, but everything up to this point is the same. Now, this is just integral from minus infinity to infinity of f of x, e to the, sorry, f of x, wx, e to the minus ikx, dx, where k is real. Okay? And now if we expand e to the minus ikx, in a power series, then using that, the inner product of f with the xm is 0, tells you that gk is equal to what?
0. Sorry, just guessing.
No, that's right. Okay?
Okay.
Yeah.
Couple questions.
Sure.
So going back to the bottom line on the left,
Yeah.
is which are we substituting for which? The xm's or the qm's? Like, which is approximating which?
Well, right now we're just saying, so we're saying that since the qn's are superpositions of the xm's, then the xm's are also superpositions of the
Oh,
qn's.
it goes both ways.
Yeah, it goes both ways. And it's not an approximation by any stretch.
It's just, okay.
Yeah.
And then, what's real in the inner product? Is it the k?
Yeah.
Okay,
So, yeah, sorry, this arrow is pointing to k.
that's what I thought. Just wanted to make sure.
Okay, so, and this is for all k, gk equals 0 for all k. Now later on in the course, what we will discover, so I can't prove this now, you'll just have to take this as a result, is if this thing equals 0 for all k's, then that means that fxwx equals 0. Okay? Right now we just have to accept that result and we'll actually prove it on Tuesday of next week. Okay? But of course, this is just the weight in the inner product. The weight can be 0 in certain regions. If we're working on an interval of 0 to 1, then the weight in our inner product can just be 0 until 0, and then you have some non-zero weight, it might be 1, and then beyond 1 it's 0 again. So when the weight is 0, fx can be anything, but in the region in which the weight is greater than 0, fx has to be 0. Okay? But if you have a region where the weight is greater than 0, then you're working on an interval anyway. Okay? So in the end, fx equals 0 almost everywhere. So the space of Sturm-Liouville polynomials is complete. All right? Any questions? Yeah.
Can that integral be 0 if the product of the functions is not even? Because I'm thinking if it is even, then it's definitely 0.
If the product of the functions is 0, or is even?
Right, or odd.
What
maybe
about that?
Backwards. Including that, I mean the whole product in the integral.
It's for all k.
Yeah, it's for all k.
I don't think it's possible to make that even for all k.
Yeah. Okay? Other questions? All right, now these were just some follow-up details on the Sturm-Liouville story. Now we are going to regress a couple of sections earlier, and we're going to see how Fourier falls into this story. And I know that Fourier series are things that you've all gotten your hands dirty with, and we will be proving some of the more mathematical aspects of them. All right, so we're headed for Fourier. But we're going to start with Sturm-Liouville. Or sorry, actually we're going to go back to Verstral. Okay, so it turns out that we can largely get most of the Fourier story, all right, out of the Verstral, which is again a story that's based on polynomials. So I'm going to write down a gentle variation on the Verstral theorem. The original theorem is also written in these notes, but I don't want to write that much, so I'm going to write down a gentle extension of it to the following. If f of x1, x2, xk, so for those of you who might or might not remember, the Verstral theorem was originally posed in terms of a function of one variable. Clearly we're going to multivariable functions. Is continuous in each, oh goodness, in each variable over the range. We can have different ranges for different variables. then there exists a sequence of polynomials Pn, and I'll do a capital M here, such that the limit as n goes to infinity of Pn is equal to the limit as n goes to infinity of the sum of nm p from 0 up to n a n m p x n 1 x m 2 x k p. Which is the function f(x, k). Okay.
Question,
Yeah.
can you explain the notation under the sequence in the A?
So these are so we're basically doing polynomials,
Yeah.
right, of the different coordinates,
Mm-hmm.
where we're allowing them to have different powers.
Oh, okay.
Okay, so this is summing over all values of n, m, and p. So like I can do, just xk by setting n, m, all the other powers to 0, and then just having p equals 1.
Okay.
That's an option here. Of course, I can have all of them be to the first power.
Oh, and then A has a unique indice for each combination.
Yes.
Got it.
Yes, okay. Now remember, this is a sequence, so these coefficients, as I increase n, these coefficients can change. This is not a series. All right? So, yeah, I mean, you probably want to go back to our discussion of Verstral and using it to build these sequences in order to get this to make a little bit more sense. But we're actually just going to take this as a starting point. We're not going to play with this that much, okay? One important observation, though, is that there is a convergence from the PNs to the F, and the convergence is uniform. Okay, that's an important observation which we're going to come back to later. There's more black markers. Black markers fading. All right. Okay, so what we're going to do is we're going to take k equal to 2. So we're just going to consider polynomials with 2 variables. And so we've got Pn of x1, x2 is equal to the sum nm equals 0 to n of a, n, m, n, x1 to the n, x2 to the m. And now what we can do is we can restrict x1 and x2, okay, which you can generally think of as the coordinates of R2, two-dimensional Riemann space. Restrict x1 and x2 to lie on the unit circle. Okay? If we do that, then we can define x1 as cosine theta, and x2 as sine theta. Hopefully this should be relatively obvious. Okay, then we have a function of cosine theta and sine theta, okay, which of course we could just call a function of theta, equals the limit as n goes to infinity of the sum of n and m equals 0 to n, a n m m cosine n theta sine m theta, where based on the fact that we're using sine and cosine, it immediately tells us that the function is periodic. Okay? And then what we can do is we can go ahead and use the good old Euler expression, relating sine and cosine to complex exponentials. All right? I won't go through the details of that. I'm rather just going to write down the result. I'm going to replace theta by x to make it a more general language. Again, we're going to use the relation between exponentials of complex numbers and sine and cosine. And we're also going to throw in a factor, an overall factor of 1 over 2 pi to the, or 1 over root 2 pi. And we get the following. Okay? Now, what I can conclude from this is the following. That f and x, which you can write either in terms of the exponentials or in terms of sines and cosines, this is now a sequence is a uniform approximation. Okay? All right? Yeah.
What is uniform?
I'm actually going to review the measures of convergence in just a minute because I'm going to talk about the convergence in more detail. Okay? So if you can just hold off. So all I'm using is the consequence of Verstral, that the convergence is uniform.
Okay.
Okay?
Right.
All right, now, first observation. This is only going to work if the function is periodic. Okay? And this, of course, means if I'm on an interval, say 0 to 1, then f of 0 has to equal f of 1. Okay? Now, I'd like to get away from periodic functions necessarily, and there is a means in which we can do that. So consider the following. So consider the line. Okay? Does the line satisfy this? No, it doesn't. Okay. So, well, wait a minute. I can approximate the line by something which satisfies this. Check this out. Okay?
Okay.
Because this red line has the same values at 0 and 1. Okay? Now, there's an interesting observation between these. First of all, clearly Rx, that's the red line, minus the blue line, the magnitude of the red line minus the blue line is less than epsilon for any epsilon, which is epsilon's a positive number, right?
Yes? What,
No.
what you're saying?
Is the difference between the red line and the blue line, for any value of x in this interval, is it less than any epsilon that I choose, no matter how small? Shit, no. I mean, look at this. At 0, it's going from 1 down to So no, this is not going to hold. Okay. However, the integral of the square of Rx minus Bx can be made as small as you like just by pushing this red closer and closer to the axis. Yes?
Why don't we just say equals 0? Like, why say less than epsilon?
Well, this is a convergence.
Okay.
I mean, so in the limit, you would say this does equal 0, but we're just talking about the convergence right now. Okay? But does everybody understand why this can hold where this can't? Okay, I mean, this is the area between these two curves, and that can be made arbitrarily small just by forming this red curve closer and closer to this axis and along that axis, right? Okay? Now, an important observation. What kind of convergence requires that to work out? Uniform or pointwise. What kind of convergence only requires that to work out? Convergence in the mean. Okay? So, in the case on the board, we would say that the red converges in the mean to the blue curve. But of course, this has an immediate implication for this. So what we can say is, and I'm going to, I'll get rid of this. What we can say is, any function g of x, not f of x, g of x over an interval can be approximated in the mean by a periodic function, which we'll call f of x, over the same interval. Okay? So we have a sequence which uniformly converges to periodic functions. The periodic functions can approximate non-periodic functions in the mean. So that means that the sequence f n x can approximate any function in the mean. Okay? Now, if you recall that any function in Hilbert space, and remember Hilbert space is defined as the set of square integrable functions, any function in Hilbert space can be approximated in the mean by a continuous function. What this means is that any function in Hilbert space can be approximated in the mean by this sequence. Okay? So this is our final result for now. Okay. Now, these are sequences which are approximating functions in Hilbert space. But you might ask, well, what about series? After all, I did write the name Fourier up here. How many of you know about the Fourier sequence? Who knows about the Fourier sequence? Who knows about the Fourier series? Okay, so trying to draw the distinction out of you, okay? So let me dip into the Fourier series for a moment. Yeah. Okay, so we showed some time ago, as an example in class, that this constitutes an orthonormal set. Which we will for now just call Tn. Okay, so we've already shown that these are orthonormal. This was done on the interval from minus pi to pi with a weight function of 1. And everything I'm going to do from now on, well, at least today and Tuesday of next week, is work with a weight function of 1. So don't worry about complex weight functions. All right, so we showed that this was orthonormal, but we didn't show that it was complete. We actually showed this before we had talked about the criteria for completeness. So let's very quickly show that this is a complete set. And how are we going to go about doing that? By showing that it is closed. Yes. Yes. Okay, so here we go. We'll repeat the argument. Although it will differ at a certain point. All right. So closed implies complete. Closed if a function interproducted with any of the tn's equals 0 implies that f equals 0 almost everywhere. Which I'm just going to say f equals 0. And then almost everywhere will always come along for the ride. Okay, for all n. Now, once again, these tn's are superpositions of these trigonometric functions, right? So these trigonometric functions can be written as superpositions of the tn's. Well, if one of them has an inner product which vanishes, so does the other. Okay? Now, what we can consider is the magnitude of the difference between the function we're approximating and these Fn trigonometric functions. Well, this is going to be f squared minus 2 f Fn plus Fn squared all to the 1/2 is less than epsilon. Okay. That's 0. But this, of course, if this combination has to be less than an arbitrarily chosen epsilon, then what does Fn and f magnitude squared have to equal? 0. Okay? Almost everywhere. Okay. Hence, this set is complete. This set is closed. Therefore, it's complete. Okay? So these tn's form a complete orthonormal set. And then, of course, we have the following. We can approximate in the mean an arbitrary f of x by an infinite series Tn, that is f of x equals with the dot means it converges in the mean, sum over n equals minus infinity to infinity of Cn Tnx, which is just the sum from n equals minus infinity to infinity of Cn over 2 pi to the 1/2 e to the I n x or a naught over 2 plus the sum from n equals 1 to infinity an cosine nx plus bn sine nx. Okay? And in this case, the coefficients we can get just by taking the inner product of Tn with f. Okay? And then we can write down a similar expression using the cosine and sine functions instead. Okay? So this together is what is called the Fourier series. Notice it is a series, and it has that important distinction between being a series and a sequence that the coefficients are all constant. If you extend n to larger and larger values, the earlier coefficients do not change. That is not the case for a sequence. Okay? All right, one more quick thing, and then we'll move on. As a result of this, since it's complete, we know that if we do the inner product of the function with itself, which is of course the integral from minus pi to pi of the magnitude of f squared dx, then this is equal to the sum from minus infinity to infinity of cn squared, which, and this will be useful later on, in terms of the sine and cosine expansion, is pi a naught squared over 2 plus the sum from n equals 1 to infinity of a n squared plus b n squared. Okay? All right, so, okay, so what have we got? Well, we have a trigonometric sequence which converges uniformly to any continuous function f of x as long as the function enjoys that condition. Okay. I'm not saying the condition has to be periodic throughout all of x. I'm just saying it has to satisfy this, and I'll give you an example of why that's an important distinction in a minute. Okay? So we have the sequence, which converges uniformly as long as that's satisfied. And then we have the Fourier series, which only converges in the mean. Okay? Now, clearly these are very closely connected. One is a sequence, has these changing coefficients, but its convergence is uniform. One is a series with these constant coefficients, but its convergence is only in the mean. It seems like we should be able to do better than that. It seems like we should be able to argue that the Fourier series converges uniformly, and it turns out that it does, given certain restrictions. So, let me state the theorem with the restrictions, and we will prove it. So what we have is the following. The convergence of the Fourier series to f of x is uniform in minus pi f of x is continuous. And if its derivative is pointwise, is piecewise continuous. And f minus pi equals f pi. Okay? We can add in one more comment. If f of x plus 2 pi is equal to f of x, then it's uniformly convergent everywhere. Okay? Oh, all these markers are dying on me. Okay. Now, what exactly do I mean here? Well, we could have a function which on the interval from, let's say, minus pi to pi satisfies this condition, but it's not periodic. Okay? What this is saying is if all I'm doing is focusing on this interval, then I can approximate this function by a Fourier series over the interval. Okay? But of course, if the function is truly periodic, oops. Okay. Then all we have to do is prove within one interval that this is uniformly convergent, and then we just tape it to all the others. And that makes it everywhere. Okay, so this is kind of a trivial extension. So what we really want to focus on is the interval. All right? Okay, so what I'm going to do is I'm going to work out, whoa, moving my mask. I'm going to work out some preliminary calculations. We're going to talk about convergence a bit because we're going to use a different theme of convergence, and then I'll actually work through the final aspects of the proof. So let's start by working out a few simple calculations that we'll make use of later. So first of all, we can take the derivative of the Fourier series. And if we do that, we can call it as follows. Oh my gosh. Hold on a second. Yeah, I just, one second. Just give me a second. Okay, I'm gonna play this game. Yeah. Okay. We'll just keep following this path and see if it screws up. Now, These are just labels. These are not the derivative of the coefficients that you see here. Okay? They're just labels indicating that they are part of the derivative of the function. And now we can figure out how to express these a(n) prime and bn primes. Where all I did was I evaluated this integral by integration by parts. And this, of course, is going to vanish. So this is going to just give me the integral of f times sine nx, which is going to be n times the bn coefficient. Yeah, and I didn't write those down coefficients up there earlier, which these are the ones I wanted to write, not the cn's. Yeah, so using the same idea that we used here to get the cn's, okay, we can also get the coefficients using the trigonometric functions. And in that case, if we had actually worked it out, we would have gotten a(n) is 1 over pi, integral from minus pi to pi, f of x cosine nx, dx, and bn is 1 over pi, integral from minus pi to pi, f of x sine nx dx. Okay? So clearly this thing is just this polynomial, or it's just this coefficient bn. All right? Similarly, we can work out that bn prime is minus n times an, and a0 prime, the specific case of n equals 0, is just 0. And we'll regret it soon. Okay. All right. Now, since f prime is piecewise continuous derivative, since f prime is piecewise continuous, and since the functions form a complete set, we can set f prime equal to pi a naught prime squared over 2 plus the sum from n equals 1 to infinity of a(n) prime squared plus b(n) prime squared. And that is going to end up giving us a(n) squared, b(n) squared plus a(n) squared, given these relations. All right?
Is the prime on the f a derivative?
Say again?
Is the f prime a derivative?
Yes. Okay. I mean, this expression just comes from using this form for the f primes. And then we're just using those relations between the prime coefficients and the regular coefficients. Okay. Now, here is the meat of this discussion, the comparison of convergences. So remember, and I'm not going to write these on the board because you should in some sense recall them. So this is just a set of calculations that give us some results which will be useful. Okay? And yeah, I'm going to try and get rid of most of this. All right, so recall that for pointwise convergence, okay, so for pointwise convergence, you basically have that the function you're converging to minus the sequence of functions, okay, the difference has to be less than an epsilon, where for pointwise, so the difference has to be less than epsilon for n larger than some n which depends on both epsilon and x. Okay? For uniform convergence, the number above which n must take in order for this to be smaller than epsilon depends only on epsilon itself. Okay? Whereas for mean, for convergence in the mean, we of course know that we don't consider this difference, but rather we consider the integral. Okay? For n larger than some integer, which is a function of epsilon. Okay, so those are the three convergences that we've talked about so far. But one of the things I want you to notice is that in all three cases, you're utilizing, to state the criteria for convergence, the function that you're converging to. Now, you should, in some sense, be able to talk about the convergence of a function just by talking about the comparison between different the convergence of a sequence, just by how different elements of the sequence are behaving. And you might not remember it because we used it in a slightly different context, but this is what the Koshi condition gives us. So what we're going to use today is the Koshi condition. And the Koshi condition says the following. The sequence Hn of x converges uniformly on the interval AB if for every epsilon greater than 0, there exists an n which is only a function of epsilon, such that for all r and s greater than this integer n, and for all points x on the interval from a to b, we have that hr of x minus hs of x is less than epsilon. Okay? We don't actually have to know what these sequences converging to. This is a statement about the uniform convergence to something just based on how different elements of the sequence are comparing. Okay? Now, if I prove that the Fourier series satisfies this Koshi condition for convergence, isn't that only half the story? Because don't we need to know what function it's converging to? just gonna pick someone else in the room, Jacob.
I'm sorry, question?
Jacob, we're going to use this Koshi condition to prove that the Fourier series is convergent. But convergent to what? This Koshi sequence doesn't actually tell you, or doesn't involve the function to which you're converging.
I guess just to itself or I guess R, or I guess little n is included.
So this will just show that it converges to something. It won't tell you what it's converging to. How are we going to figure out what it's converging to? Well, if I knew one of these, I could say, oh, it's just, that function that's in that criterion for convergence, right? Well, hold on. Aren't the Fourier series convergent in the mean already? We're just trying to promote this to uniform convergence.
Right.
So if it's already convergent in the mean, you can already identify what function it's converging to from this condition. And then we're just going to use Koshi to bump that up to uniform. Okay? Does that make sense? All right, good. So here we go. I'm just going to bang this out. Yeah, it's going to be a little bit ugly, but we'll just get through it. All right. I'm going to erase what I'm trying to prove. Here we go. So first of all, to form a sequence as opposed to a series, oh my God. Hopefully this one will work. Wow, am I writing that much on the board? Okay, to form a sequence, oh boy. Okay, we'll just switch to blue. Huh? If you got one, that would be very helpful. Okay.
Yeah.
Okay. So here we go. So first of all, we need a sequence, not a series. But we can form a sequence from a partial sum of the series. Okay? Everybody recognize that? That's a sequence. Okay? All right. Then, what I want to do is I want to compare two terms in this sequence. On board? All right, here we go. First of all, these terms will cancel. There's subtracting, so those terms go away. And it turns out that, and I'm just going to assume that n is larger than m in this. So you're going to start from p equals 1, and you're going to go up to n in this sum, and you're going to go up to m in this sum. These are the same sums, so a lot of the early entries into the sums will just cancel when you subtract. In fact, the only things that won't get canceled are the n's that are larger than m. So therefore, we can say that this is sum over p equals m plus 1 to n of ap cosine px plus bp sine px. Okay? Which we can also write in the following slick form. One over p, and then put a p in turn of each term. Okay? So wonderful multiplication by the number 1. And the reason we do that is if you look at this expression for a moment, This is a lot like taking the inner product of two vectors where the components are labeled by p, right? I'm taking the vector 1 over p, and I'm doing the inner product of it with this function of p given by this. And then I'm just summing over the different p's. Okay? Does everybody kind of see that? It's not the actual inner product on this space. This is a functional space. But this combination of this coefficient 1 over p with this goes a p at a time, and then it adds them all together. So it's a lot like taking an inner product. And the reason I say that is because you have the Schwarz inequality, which says that this is definitely less than or equal to 1 over p inner producted with itself times f of p inner producted with itself. Okay? So this means that we can immediately say that the difference is less than or equal to the sum from p equals n plus 1 to n of 1 over p square root, or sorry, p squared, because this is less than the inner product of 1 over p with itself, times the square root, and this is just going to be the inner product of fp with itself, of sum p equals n plus 1 to n of p a p cosine px plus p bp sine of px squared. Okay? Now this guy right here, we can actually rewrite. We can say this is p squared times ap cosine px plus bp sine px, quantity squared, which is p squared times the magnitude of ap squared plus bp squared times the cosine of px minus the inverse tangent of bp over ap. Okay? We're just rewriting this term in this form. Now, this thing right here is necessarily less than what? Less than or equal to what? Well, how about that? I mean, cosine is less than or equal to 1. So this combination, if you need to go, go. Yeah. This combination is less than or equal to this. Okay? Now, oh, wait a minute, hold on. So this is less than or equal to something very, very similar. I mean, these are all positive contributions, right? Over the range from p equals n plus 1 to n. Well, this sum is definitely smaller than this sum. Right? Similarly, this sum, which is the combination of positive things, this sum is definitely less than the unrestricted sum. Okay? Wait a minute. Okay, so this this looks like this. So what we can say is that this is less than the sum from p equals 1 to infinity, 1 over p squared, square root of 1 over pi, integral from minus pi to pi of the magnitude of the derivative of f squared dx. Okay? I'm just going to erase this off. I don't need it later on. We're going to call this m. Okay? So what we have so far is that the difference in two elements of this sequence must be less than this, the square root of this sum, plus this guy, or times that guy. Okay? Now it turns out that 1 over p squared, or the sum of 1 over p squared converges. And so this must satisfy a Koshi condition. So what we can say is for 1 over p squared, if I take two elements of the sequence, all right, where this is of course the sum over p equals m plus 1 to n of 1 over p squared. Okay, it's the same thing that we have happen up here. This is less than epsilon for n and m larger than some integer. So I'm saying this is Cauchy convergent. So we're using the Cauchy convergence. Now what I'm going to do is do a following renaming. What we're going to do is we're going to say, okay, instead of epsilon here, why don't I call this epsilon squared over m squared? Because this m is a finite number. It's not infinite. It doesn't diverge. So I can just soak it into the specification of epsilon. So I can give you that. Okay? What can we say about the difference of Sn minus Sn now?
It's less than epsilon.
Okay? So the sequence converges uniformly. All right? So what we just proved is that the Fourier series, which we started out by observing that through its construction only converged in the mean, actually does converge uniformly as long as this is satisfied. And you're talking about piecewise continuous derivatives. Okay? All right, more next time. Man, that was going to be a smooth move.
It was. I was disappointed with myself.
Is the inner product defined with square roots? I'm like confused. The magnitude is.
Yeah, the magnitude.